Good morning, everyone. Today is March 18th, and this is the John Chappell Natural Philosophy Society Science Chat. And this is where we can discuss all things related to science and alternative science. And today we have a special guest, Clive Tickner, and he is going to be talking about topics about relativity. So let's see, I'm going to put his presentation up and I'll let him take it away. All right, go ahead, Clive.
Good. Hi, good morning or good afternoon if you're in England like like I am. I want to speak about a lot of flaws that I personally find as a result of ideas that have been extrapolated from special relativity. So I'm going to start with this really simple one, simple idea. This is the notion I'm sure you're all familiar with, whereby two observers are employed. The observer who's traveling in the carriage at the top sees a light bounce up and down from between two mirrors as the train travels to the left. And the notion that the outside observer sees those mirrors move during the passage of time that the pulse of light takes. And so the diagonal distance is considered to be the outside viewer, and the upright distance is meant to be the traveling viewer. And here we have the Pythagorean theorem, which enables us to work out d, and there's the difference between the outside observer understanding of time and the upright observer's understanding of time. Now, this is there's a weakness in this straight away, and that is it involves the person who's traveling to travel at a sort of perpendicular direction as opposed from where the outside observer is looking. And you can see that if we introduce other observers, the diagonal angle changes. For a 45 degree, of course, the angle's less, and if the observer is looking straight down the track, the outside one, he will see that diagonal as an upright line. So already there's a weakness to this idea, but it's not as weak as this. And my claim is that if you have two mirrors like this and they move along, like in this drawing, the light is not dragged along by the carriage. The light is unaffected by the inertial frame of the carriage. And so as the mirror moves, it gradually moves out of the way of the light and it escapes. So my point from this is that to apply this hypotenuse to work out the difference in time between a traveling observer and an outside observer is complete nonsense. Now, just to make it more clear, this is England where I am, and I am here imagining two giant mirrors on sea level about 500 miles apart, and they are set on a sort of geared track with cogwheels, and a signal can come from a midpoint and tell these mirrors to move along the geared track, and they will move completely synchronously. This is the idea. And I'm sure you can see that if there's a light bouncing between the two in the left-hand diagram, those mirrors are just going to move out the way of that path and it will escape.
Clive, Harry Ricker here.
Oh, hi.
I don't see the diagram. Am I the only one not seeing the diagram?
Oh, that's bad news. Is Franklin there to correct that?
Well, I can see the diagram. Bill, can you see the diagrams?
No, it says loading on my PC.
Does it?
Yeah, that's what I have.
All right. Well, we're gonna have to. Can you let me try and reload the diagram? We got to make sure we get that.
Yeah, it's gonna be important.
Well, let's see here. Let's load that one, and then let me reload.
I see that.
Okay, so you see that one? Okay, so let's reload the PowerPoint. Do you see it?
No.
No. Let's try something else. Let's try loading in your other PowerPoint.
Maybe the PowerPoint is much bigger. It's not just a single screen.
Do you see this PowerPoint?
Clive, certainly have got it, and that's the first one of my of the second.
So Clive, you can see it, right? Bill, can you see the slide?
See that fine.
You can see that slide?
Yes.
Okay, let me try and load back the first one.
I can't see it here. I have no idea what's going on.
Okay, I'm going back to my first board.
So Clive can see it, so it's definitely getting out remotely. Does anybody else see the slides? Like Jim, do you see the slides?
I can see it.
So the only thing I could suggest is you exit the meeting and re-enter, because it seems like some people can see it and some people cannot. So why don't you try that quick? Try, if you can't see the slides, exit the meeting and then come back.
Yes, it's going to be a disadvantage if the slides don't read.
All right, let's see. Hopefully that helps. Yeah, I've never seen that happen before, where some people can see the slides and some people cannot.
I still have it.
They should be back in a moment. So in your diagram there, you were showing that if only one of the mirrors moved, then obviously the mirror would move out of the light beam.
Well, if both of them move together, I was just coming onto a slide of a little experiment that I did. If they both move together, the light doesn't know that the mirrors are moving. And so they obviously, there's no tactile connections, and they obviously just, the mirror slides sideways and the light doesn't know until suddenly there's nothing to reflect it.
Well, it certainly is totally clear that if you only have one of the mirrors moving, that mirror will certainly move out of the way. I don't think anyone would ever doubt that.
No.
But when both mirrors move, then, I mean, some people were talking about that somehow the light takes on the
I'm going to
kinetic
show
energy
you a
of the
little,
mirror.
hopefully, when everyone's back on, I'll show you a little experiment that proves this.
All right, I like experiments. Experiments are good.
Yeah.
Because otherwise it's all talk.
Well, exactly.
And it's like all of these relativity discussions usually degrade into something that just goes in circles.
Yes, this won't.
Harry calls it irksome.
Yeah.
Okay, Bill, can you see the slides now?
Yes, I think something was being loaded on my PC. So I just turned it on, and download an update or something, and that may have stopped it from being able to load.
All right, Harry's back. Can you see the slides now, Harry?
No.
No.
Okay, proceed. I don't know what the problem is.
Well, Harry, I suppose I could send you the presentations itself. You could, I don't know, kind of follow along.
Yeah, that's a disadvantage if you can't see stuff.
Shall I send you the presentation, Harry? If you could put that on a separate window, and Clive could just tell you what page he's on, I suppose. That might help. Or maybe it will magically show up after a while. Oh, good. See, it magically showed up.
I have no idea what's going on. All right, I see it now.
You've got it? It's really important, Harry.
Huh?
Okay, so everyone can see the presentation now, right? Okay.
Didn't
So,
get any no's.
so let's
Okay.
go on then.
Right. Okay. So first of all, I started by showing what the common understanding of moving mirrors is. That there's a difference between what the traveling observer sees and the outside observer. And then I tried to claim that after showing this little diagram that we're all familiar with, where d equals the hypotenuse, and that's what the traveling observer, the outside observer sees, and the traveling observer sees light traveling at where L is. And then I came to this, where I said that it's a weak thing to start with, because it relies upon the railway track being perpendicular to the viewer. And if we introduce other observers, one at 45 degrees and one looking down the line, you can see that the diagonal line, the hypotenuse, gradually flattens out. And so by introducing extra observers, it starts to show that this is nonsense. But more so is that I maintain that if there are two mirrors and a light reflects between it, as in this drawing, when the mirrors move to the left, the light escapes. There is nothing to pull that light along with the mirrors. And then I gave this example. It's a theoretical example, obviously, it's drawing. So there are two mirrors that are set up exactly to face one another on a geared track, and they're 500 miles apart. And there is a light bouncing, a laser light bouncing between them backwards and forwards and maintaining that position relative to the mirrors. Now, a signal is given to both mirrors, to the motors, and they synchronously move to the left. And there is no way that that light beam is going to be taken to the left with the mirrors. The mirrors are going to, with both mirrors moving, they're both going to move out of the beam of the light. And as you can see here, the last time it reflects on this one's now moved out of the way and the light escapes. And so here's a little experiment done at home, and this is a light bouncing between two partially and then a front silver mirrors in a frame that's it's able to be adjusted very carefully. And you can see in the first one, the beam is slightly to the right of the mirrors, and there's 2.5 boxes showing on the table. And then there's 3 boxes showing on the table, and then 3.5. And you can see that as this frame moves to the right, with both mirrors moving together, the light moves to the left. It doesn't know that the mirrors are moving. And if I moved it one more time, the picture would show that the light's not there, but I just thought that would be rather a useless picture. Often this experience between two observers is shown in this alternative thing, where one observer is traveling in a rocket and sees a pulse going from the floor to the ceiling, like in the top picture here when it's static. And then this guy apparently would see it going zigzag, zigzag, rather like the carriages. Whereas, in fact, both people would see the rocket leaving a trail of pulses behind. So this red pulse, which is leaving here, the rocket moves forward. It doesn't know the rocket's moving. It's not affected by the inertial frame of the rocket, and it carries on moving like this, followed by all the other dots. So this is to demonstrate that light moving in an inertial frame is not affected by that inertial frame. Here we have another famous example on the left, where a person inside the carriage, there's a spark going off in the middle, and they are traveling with the carriage, and the notion is that light will hit for them the front and the back of the carriage at the same time. And I maintain that this too is rubbish, because on the right-hand drawing, we see that the position of the spark in space relative to the railway track is down this line here. So as this carriage moves forward, the source moves forward with the carriage, but the source is now, like the carriage, independent of this light beam. And the light beam expands around the point in space where it originated. So when we get right down here, this is the first time when the light hits the far end of the carriage. And this happens for both the inner traveling observer and the outer observer. And this is contrary to a lot of scientific thought that believes that you can work out a difference between these two observers. And if you imagine that that carriage has got completely transparent walls, then this is what you will see. They both will see the light hitting the end carriage here, having hit the other wall here. Now, this idea whereby the flash can travel and hit both ends at once has been used, and in my examples, I'm going to talk about the work of Wolfgang Rindler, who describes relativity, and how from his book Relativity, and he is now I'm going to show his explanation for time dilation. So here's his first mistake. He is moving his spark along, and the expanding light, he is moving it along with the plane. Here is how it should be. The red dot here is the source that's moving with the plane, and it's now irrelevant to the expansion of the sphere of light. And to demonstrate that further, I show a spaceship traveling in space, and a spark of light, it goes on inside it in the middle. But this spaceship could be transparent. Maybe this light is not in the spaceship, it's behind, but we're seeing it because it's aligned. So the spaceship carries on traveling, and whether the spark is inside or outside the spaceship, it is unaffected by the motion of the spaceship. The point source stays in the same place from which the light expands. Now this error has given it's given rise to a misconception about how Rindler especially tries to work out the difference in time between two observers. Here is a drawing of two observers passing in spaceships, and the top guy, his clock says 10 past 10, but he sees this guy's as 10 o'clock. He sees it behind because relative to him, he is in motion. This one, because of the need to make a reciprocal reaction, this guy sees his as 10 o'clock and he sees his at 10 past 10. And now all this seems perfectly straightforward with, I don't know whether you can see it or whether something's written on that, but it's, I've got the arrows over mine. So it says, the time dilation, each astronaut sees the other's clock as running slow. Now, Rindler does something rather complicated to make this work. So he does differentiate between what the outside observer and the inside observer sees. He does admit that the outside observer would see the flash of light, which we have in that last drawing. This was the source. It was the flash went when it was here. Now the planes move forward to here. So the outside observer sees it taking 5 seconds to reach 5 units of time. I beg your pardon. Rindler doesn't say times, he says units of time. And he would say that it would expand around the initial point of the flash. Now, the odd thing is that having established that it takes 3 seconds to hit the back for the outside observer, he maintains that at that moment, it's only, if it took 3 units of time there, he maintains it will only be 1 unit of time at the head of the plane because the light has not yet hit there for the outside observer. Now, he then extrapolates further, having decided that there's
excuse me, can we go back to the, I didn't really understand what you're saying here. Can you go over this again a little more slowly?
Okay, sure.
The internet, sometimes it garbles what you say.
Okay, sorry. Okay, well, Rindler maintains that the inside traveling observer will see light hit the front and the back at the same time. And he's given that, he gives it a time, 3 units.
Oh, okay. All right, got it.
Of time. Now, the outside observer, he does agree, will not, that the phenomena of where the light hits first, which I maintain is for everybody, he says, okay, the light will first of all hit the back, and then it will carry on expanding for 5 units of time, until it hits the front. So when he's dealing with the view of the outside observer, he's maintaining that he will see that hit here at 3 units of time. But he maintains that because the light has yet to hit here, and that's got to take 3 units time more, at the time here, there must be a time difference for Rindler between, believe it or not, the front and the back of the plane. So he gives the back of the plane 3 units, and where I've given it 5, because I think that's correct, he gives it 1 unit of time. So it is a very strange thought, but it's commonplace in my reading of physics about trying to work out diagrammatically the time difference between traveling observers. So he goes on to say, having maintained that the difference in time inside each plane is like this, he invents a second plane coming and passing where the same event has occurred. So now he makes out that this is passing here when their time difference is 2 units apart. And then he says reciprocally, this, when it passes, is also 2 units apart. Now, I think this is absolute nonsense, and my drawing just shows you after 3 units of time where the light on each plane will be. And of course, it doesn't affect that. If you imagine that somebody on here, each end of the plane, has got a synchronized watch, and they happen to be synchronized with these guys, the fact that they're passing, in my view, does not affect each other's time. So this is what I've been saying. I don't believe that there is an actual difference in the time for 2 passing individuals. Now, I know that there are a lot of practical experiments which we are told prove time dilation. On another paper, I've been through a great many of these. And I'm just going to deal with 2 here and tell you what the faults of the experiments are. So I'm sure we know that Rossi and Hall found extended lifetime for muons, and also the synchrotron at Brookhaven discovered that muons went round their circuit lap 400 times when it was expected of their decay time that they would only go around 15 times. So their claim is that the extended lifetime of the muon is down to time dilation, that for the muon, and actually if a human being could travel with it, their time would extend by about 27 times. They would, their life would slow down, and they would have this 27 times expansion. However, click onto the next one. At the time when this was being done at Brookhaven, Stanford were doing an experiment to determine changes of mass of accelerated objects. And as it happens, they were also accelerating muons down a 17 kilometer tube. And their interesting conclusion was that at the end of the tube, these muons had additional mass of 40,000 times. This is this mass, of course, is due to energy, and kinetic energy is associated with mass. So my claim is that the extended lifetime for these muons was due to a much larger mass having to decay. So they start decaying, and as they go round and round the synchrotron, their mass increases, and that takes this further time to decay.
But Clive, can I ask a question here?
Yes, of course you can.
It's like, so the amount of predicted time dilation that matched the relativity formulas?
Yes.
It wasn't random, but do you have an equivalent formula for time dilation due to increase in mass?
No, I don't. And I think you'll see by the end that I'm not over enamored with maths. I think that they can maths can confuse things, and there are, I've got another paper on where maths has been misused, but for me, that maths is not a great answer to things. But for me, it was enough to know that this increase in mass of the same stream of muons that Stanford is sending down a tube was expanded by 40,000 times. There is no evidence on the synchrotron experiment of an increased mass. They don't deal with it, and they weren't investigating increased mass. So all their figures are just down to the number of circuits that the accelerated muon was able to do.
Well, I think the point that I'm trying to make is that the time dilation could have been anything. If the time dilation didn't happen due to that hypotenuse formula, then it might not be 27. It might be 30 or something.
Oh, okay. Yes. No. I'm not wedded. I'm not wedded to that number. It's just that their claim was that the muon's life was extended just because of time dilation. But of course, if one was to apply a sort of reciprocal experiment, whereby, as Galileo says, anything could be moving or static. So if we say that the muon is static, then you've got a whole bunch of scientists who are flying around at near light speed. For me, because of the sort of nonsense of that thought, time dilation cancels out. If both the muon could be moving and the scientist not, and vice versa, I'd say that if there was time dilation, it would occur in both events, and it would therefore cancel out.
Now, one other difference I wanted to mention was that, so I can totally understand your light clock theory, your light clock explanation about the light would bounce out.
Okay.
But the muon seems different because it is actually physically traveling the path that it's taking. So unlike the light, it can't bounce out. So I could see that actually traveling the extra distance.
Oh yes, yes. The light doesn't bounce out. It's held in by a ring of magnets. So there is. I'm leaving behind at the moment my notion that light can't bounce between two mirrors, and coming on to trying to say how I want to refute the experiments that are done to prove time dilation. So my first pictures were to show why I think that the hypotenuse is a misleading way of looking at the differences in time experience between two observers. And I'm moving on to say that practical experiments also fail, as does the theory, in proving time dilation.
Yeah, you had your experiment there with the green light. So was that experiment actually moving? So I think you'd have to move that experiment pretty fast, like thousands and thousands of miles per hour to get the result that you saw in your picture there.
Yes. So with the laser light bouncing between these front silver mirrors, I physically moved the frame across the table, and it was the light stayed where it was. So this is to back up my idea that in a carriage, when you've got two mirrors, this is obviously on the flat, but two upright mirrors makes no difference. When you've got two mirrors and light's bouncing between them, when you move the mirrors, the light escapes.
So you're just moving the closer mirror to the right.
No. They are both.
They're both moving.
Yeah, that is a solid frame. This is a solid box frame, and there's a front silver mirror at that end, and this is a front silver mirror.
So how fast is this moving?
Well, the green light is moving at the speed of light.
But how fast is the box moving?
Well, I just grabbed hold of the two ends here and pulled it across the table. I mean, I don't know. I've moved it very slowly because I had to keep the two mirrors I thought that if I spun the mirrors and that would be a different experiment. So I've just pulled it. So it doesn't matter how fast the frame is going. The two parallel mirrors are united. This is an absolutely solid frame, and the two mirrors are absolutely solid within it. So when I pull here, both mirrors and the frame all move across the table.
I don't understand. I mean, if you're not, you'd have to move the whole table.
Well, no, I left the table still because that's the way that you can see that the frame has moved across it. There's 2.5 squares here, there's 3 squares revealed here, and there's 3.5 there, which shows that between the still photographs, I pulled the frame across the table.
So where's the source of the laser? Is that like behind the first mirror in the back?
The laser was this mirror here. The very edge is partially silvered, and the rest is front silvered. So the laser was aimed through this partially silvered at a very, very fine angle, whereupon it was trapped then between the two front silvered mirrors.
So the laser is coming from the near, like the laser is off screen, but it'd be like in front of.
Well, it doesn't matter where it is; it's switched off. This light is just as we've talked about in the carriage. It's a light just bouncing between. It's a contained light moving between two mirrors.
Well, that can't be. I mean, you don't have equipment that's fast enough to observe a pulse that short. I don't think. I mean, you have to have the laser turned on the whole time while you're taking these pictures.
Well, by introducing it at a very these mirrors are very fine. It can be very finely tuned. So if you introduce a laser through the partially silvered mirror, when it comes back, it then hits the edge of the front silvered mirror, and when that goes back that end, because of the angle of this, that can trap the light.
I don't know. I still don't understand, but go on anyway. So
okay.
Unless anyone has any questions, but I still don't see.
I can come back to that afterwards.
I can explain the muon decay changing. I'm an intermediate energy theoretical physicist. Worked a lot with muons and pions and kaons.
Okay.
What happens is the binding energy of the muon increases according to Lenz's law, and so it makes the decay slower. It takes longer to decay. And
I think that's what I'm.
That's
saying,
what you're seeing, but it's not due to, it's a physical thing due to Lenz's law, which has to do with electrical feedback and that kind of thing for motion. Yeah. And so it doesn't have anything to do with relativity theory.
Well, that's exactly my point, that the synchrotron experiment is used to explain time dilation. They claim from that experiment that it's due to time dilation that the muons have an extended lifetime. I'm going to go on to the other really famous experiment. I mean, you go on the internet, you read books, everybody quotes Haefel and Keating, even though that later in their lives they said it didn't come to anything. So these two scientists flew 4 cesium atomic clocks on quite a long flight in 1971. Now, it's interesting that they took 4 atomic clocks because they took them because it was to iron out any discrepancies. And they wanted to compare this with a ground-based atomic clock. Now, if they are allowing for the fact that they are taking 4 to cover any discrepancies, then presumably you can say, well, there's probably a discrepancy between any of those 4s and the one on Earth. However, after all their flying, the result they came up with was written in blue here, that if a man lived for 100 years and spent all his life flying around the world, he would be younger by his stay-at-home twin by 10,000ths of a second. Well, when you work that out against a year, that is a smaller amount than the accepted differences on atomic clocks. So I'm suggesting that the whole experiment wasn't worth the airfare. And also, there was the way that the atomic clocks were looked after was incompatible with a proper experiment. On Earth, these are chilled with liquid nitrogen, and they're susceptible to atmospheric changes. And of course, the plane went through atmospheric changes. Also, it wasn't cooled to liquid nitrogen. So this is me saying that the Haefel and Keating experiment was worthless. Now, I want to talk about the predictions that time dilation allows, and I'm afraid it's going to be the twins, because the more I read about the twins, the more upset I get at the mistakes. I believe Roger Anderton said last week that there are as many results or excuses for this as there are theoretical physicists talking about it. But generally, the claim for the home twin to be older than our astronaut twin is based on the fact that the astronaut twin accelerated and decelerated during her trip. So the difference between the non-inertial frame of the astronaut and the inertial frame of the earthbound twin is what is considered to be the basic reason why there is a time difference for these two protagonists, that the astronaut is going to live longer because her time goes more slowly. Now, when this idea and similar ideas are considered in a reciprocal manner, in order to get symmetry to see whether this can be acceptable or not, the consideration is that if we say that the rocket is going to be at rest and it is the Earth that's moving back away from the rocket, so this would be the symmetry of the rocket accelerating away from the Earth, and it seems perfectly fair to consider symmetry in this example. And the idea is that if it were the Earth moving away from the rocket, the behavior of the accelerometer on the ship would not read, but if the rocket was moving away from the Earth, the accelerator would measure acceleration. Now, I'm afraid this is rubbish because of the idea of the symmetry is wrong. So the correct reciprocal events would be these. It would not be just the Earth moving away from the rocket. All the rubbish in space. Good. So in this first one, we've got the shuttle moving away from the Earth. So there's a distance here that it has traveled. And here you can see it has traveled further and the Earth is in the same place. In this one, the rocket is in the same place here, but it's been the reciprocal event. The Earth is responsible for it. The position, the Earth has moved it away. The Earth has moved away, the rocket is considered at rest. But because that it's the whole universe that is the part of the symmetry, you imagine this, the rocket being static and the universe moving away. Therefore, the accelerometer on the rocket would read in exactly the same way as if it were the rocket moving. And I've just added one here where the rocket is moving and the Earth is moving, as we can tell we can't tell which actually is the moving object if we're to believe Galileo. So from this conclusion, I say that the only that symmetry is going to be the proof why the twins is a nonsensical argument. They will both age the same time because time dilation does not occur, because if you apply the reciprocal event to this occasion, then time dilation, if it happened, would cancel out because both the rocket static and the universe moving or the universe static and the rocket moving, they are inseparable events. So here's where I've just written about it, just to show that by symmetry, with the rocket being considered at rest, then it's not just the Earth, but it's all the planets and stars moving, and the accelerometer will measure exactly the same in both instances. So the twins will maintain the same age. And just coming on to some other crazy explanations for time being different for two observers. Here's something from Roger Penrose. Now here's a traffic light, and at the top, the traffic light is approaching a pedestrian and a moving car. And in the next frame, we see that for the pedestrian, the light has traveled a third of the way down his ruler, but for the car, it's traveled the whole way. So Roger Penrose claims that time is different for these two observers. And for me, the whole concept of applying two observers to any theoretical hypothesis is in itself desperately faulty. So this is just nonsense. It only covers this because the car is moving. That's why, not because time is different for these two people. And in fact, if we were to put a flash of light at the back while the traffic light was coming at the front, you'd find the situations were being reversed, that the light would take longer to cross the car because it's moving than it does for the pedestrian because he's still. And Roger Penrose goes even further with a completely nonsensical suggestion that a person walking towards Andromeda will have a now moment that can be hours or days ahead of the person walking in the opposite direction because of intergalactic distances involved. He says that even with quite slow relative velocities between the observers, significant differences in time ordering will occur. So he suggests that when they pass one another, the now moment is simultaneous. And for one, a space fleet has been launched from Andromeda with the intent to destroy Earth, whilst the other, the decision is yet to be made to invade Earth. Well, this is such a big difference in time that the reductio ad absurdum is that for one observer, all is well with the world, but for the other, who's just walked a few yards apart, he's a smoking skeleton and the whole world is in ruins. So there are theories that are attached to time dilation which just are ridiculous, and I'm hoping to convince everybody that it's sufficiently ridiculous to kick time dilation itself into a hat. I'm going to talk very quickly about gravitational time dilation, which I'm sure you're all familiar with. So time passes more quickly the further the clock is away from a gravitational influence. So I've done a drawing here where this is further away, it's 10 past 10, and on Earth it's 10 o'clock. Now, we remember from talking about what people believe with rockets in space and Earth, that a rocket in space is traveling more slowly, that a clock in that rocket will go more slowly than a clock on Earth. So here I bring one of these rockets into low orbit, and we've got a real confusion of time. We've got the time behind for the traveling rocket, the time ahead for the guy on top of the mountain, and the proper time, 10 o'clock on Earth. So what I can't do is to make this work for me. So I believe that this proves that the whole fact of time differences everywhere is confusing and unnecessary. And as a result, I'm going to suggest, and I can't click down at the moment. Why is that? I've come to the end of this one. Franklin, I need to go on to number 2, please. Right, so I'm going to suggest that we stick to sidereal time. A clock that works in this way would click when a reference star is directly overhead each day. Propagation time is then of a fixed amount. It won't affect the rate at which any clocks count. Clocks will read whatever their height, whatever their depth, whatever their speed. Therefore, if we use the rotation of the Earth as a clock, using as our reference the position of fixed stars, all the contradictions associated with these physical problems become redundant. Clocks will continue to be in sync. And you won't have the ridiculous situation that a mountaineer can be walking into the future just by walking up a mountain. So here's a little drawing of a reference star going past, and observer A and B on the top and the bottom of the mountain, agreeing on a time. So I want to move on to length contraction, as it's so closely tied to time dilation. Length contraction being said that objects shrink in the direction of motion as they approach the speed of light. Here is the famous pole in barn hypothesis. We have a 10-foot garage and we have a 20-foot pole at rest. Then we have the pole is traveling at 80% the speed of light, which brings it down to half its length. It's now a 10-foot pole. It travels towards the garage, the barn, and momentarily it fits. Now, I'm suggesting that Einstein initially mentioned this. I think it was a car in a garage. I think he must have mentioned it as a joke, but it has been taken very seriously ever since. And this is considered to be a feasible product of length contraction. So next I look at the reciprocal event of the garage approaching the pole. So here the pole is at rest, it stays at 20 feet, and the garage, traveling at 80% the speed of light, is reduced to 5 feet. Now, the explanation is given that at the point of impact, the back of the pole does not know that the front of the pole has been hit because of the speed of all information traveling at the speed of light. So the garage is able to push this pole closer and closer until it fits like this. And this is considered to be the reciprocal and symmetrical event of the pole in the barn, which allows us all to believe in length contraction. But there is a huge difference in this example and this example. Here, the garage stays as a garage. Nothing, it doesn't get hit, doesn't get damaged, doesn't do anything. But here, the pole must be crushed because the pole is not affected at all by traveling because it's at rest. So the only way that it can fit in this garage is it's physically crushed, which means that when everything stops, when everything slows down, this pole, I'm using the wrong thing here. Are you seeing my arrow? I've just temporarily lost my.
We seem to have lost your arrow. Maybe you have to click on it again.
I think I've got it back.
There you
so
go.
Here, the only way this image could occur is if this pole is permanently crushed, so that when everything comes back to normal, like in this one, once everything stopped, this pole would spring back once it was static to 20 feet. But in this, the pole cannot move back. It is crushed. So this is not a reciprocal proof of length contraction. It just doesn't work. And what I've got here is...
Well, it does.
Sorry?
It would work because in the only thing would be the opposite, that your garage is contracted in this case instead of the pole. So just like your pole goes back to its normal length when everything stops, in the second case you could look at the garage going back and everything stops. It wouldn't matter.
Well, yes,
it would be the same. It would be the same if you had two poles approaching each other. It's still reciprocal.
Well, you see, in this one, you're right. The garage would spring back, but the pole wouldn't. Whereas in this example, they would both spring back to their correct lengths. So my claim is that this is an impoverished reciprocal event. And I've done a drawing. It may be rather difficult to see on here because of scale of what I think would happen given present physical laws. So here is the garage coming towards the 20-foot pole. Here is the moment of impact. Now, this is worked out on a graph, so all the changes are proportionally correct. So the information about the impact for the garage is my blue arrow. So here's the information about the impact moving down. But because the information hasn't reached the garage doors, the opening, if we are to believe from the other one that the pole will continue to move, then the opening of the garage will continue to move because it hasn't been told to stop by the impact. And then it's right down here when the story of the impact, when the impact says, hey, you've got to stop because we've been hit. It is right at the bottom of this. So the implication of applying physics to this is that the garage doors will continue to travel at 80% the speed of light, whilst the information of the impact tries to catch up, and it does because that's going at 100% the speed of light. So we're getting a very, very odd thing here of the garage somehow extending its volume without there being more bricks and cement, and it's just, I believe this is applying physics is what would happen, but I believe that in real life this wouldn't happen because I'm criticizing length contraction at speed. Here's another theoretical experiment with a pole going into a barn. So here we've got a camera, and before it moves, it records. Here is what the camera is seeing. It's recording a 20-foot pole against a 20-foot ruler. And here's the result. That's what we see. Now, the camera is going to travel at 80% the speed of light with the pole to here. So as the pole's entering the garage, the pole is reduced to 10 feet. And the camera is also reduced. As it's reduced, its field of view is reduced. And this is what this will see. It will see, because it's only shrunk in the direction of travel, it will show the same diameter, but it will show half its length because it's traveling with the pole, and it will show half the length of the ruler. That's what it will see. Here is a follow-up experiment where the camera A and camera B, cameras do not move. So, is everyone still getting me? I'm getting funny scrapes on my headphones. Are we still good?
Yeah, we're still good.
Great, thank you. So here, camera A films photographs the pole at full length, and here is a static camera. No, there's no movement between the cameras this time. A static camera, and it's triggered to fire as the pole crosses its field of view, and it's given a very, very, very fast shutter speed. So this camera will see the pole at its correct length. It will see the ruler at its correct length, and this will be the image that it receives. So this is a real confusion because physics has an expectation of matching records and identical conclusions for a single physical system. We've just been looking at a single physical system, but I list here all the differences that those cameras would record. And so I'm using this as an example to say that to refute the pole in the barn, I don't believe that this pole will shrink in the direction of travel. Right. I want to deal with length contraction when it's just applied to space travel. So it's commonly held belief that distances to far galaxies may be reduced by near light speed travel. Well, given that a rocket's length at takeoff may be calculated as a particular percentage of its proper journey distance, so if this is 1 billion miles and that happened to be a mile high, you get a line of 1 billion rockets. However, if the rocket is going to shrink in the direction of travel, there's going to be far more rockets end to end to make that difference. I mean, if it shrunk to half its length, you'd have 2 billion rockets. So my point is that by the length contraction applying to the rocket doesn't help the rocket get to Andromeda any more quickly, because it's got many more times its new shrunken length to travel. For example, if that's 1 billion miles and that's the rocket, what I've done is I've just shrunk it and shrunk it and shrunk it, and you can see that the ratio of the size of the rocket to the distance remains the same. So there's no advantage, even if there is such a thing as high-speed length contraction. Now, this is a quick page showing the maths that prove that different observers will consider different times taken for a trip in space. So it slightly harks back to the twins, and I'm showing it because I believe that the practical and logical way to look at these things will give you a different result from the difference that mathematics gives you. So Brian Cox, he has an example in one of his books of a journey to Andromeda taking only 50 years because of traveling at the speed of light. So here we have two observers to start with. We've got the guy on Earth who thinks it's going to take 3 billion years, and you've got the guy in the rocket, and he thinks it's going to take 50 years. Now, this to me is a prime example of the misuse of, or the only use of, two observers, because here I invent a third observer, our alien, and he's on Andromeda here. So the rocket takes off, flash, and the rocket takes 50 years and it lands beside the alien. But the light from the takeoff flash, that's got to travel 3 billion years. So this is 3 million years. So the alien is going to see the rocket land beside him, and then if he lives long enough, he's got to wait 2,999,950 years before the flash of the takeoff reaches him. I mean, it doesn't work, does it? It's just nonsense to believe that you can, just because of the speed, you can actually beat light. So Brian Cox's other observation, and also I've got a quote, a maths quote from D.F. Lorentz from An Introduction to Tensor Calculus. They both observe, I wrote to Brian Cox about this phenomenon of having the alien there, and how he would observe something different, a huge time difference in the arrival of the flash after the arrival of the rocket. And so Brian said, well, for light, space is an infinitely thin pancake. He says, like here, the space-time distance between any 2 points in the universe is 0. And this is also the conclusion of the maths of D.F. Lorentz. Now, it's all very well saying that distances are 0 for light. It's almost as if it's also almost anthropological, because it's almost as if light has got an opinion about how fast it's traveling, or it's got some knowledge. It's just it doesn't matter if light thinks that space is infinitely thin. Light does travel from, in this previous case, from the Earth to Andromeda, no matter how you consider the maths saying that space is an infinitely thin pancake. So I've got here, it's a kind of question really. The rocket propellant can't be compressed, so if things do shrink in the direction of travel, the tanks burst. Also, the controller on Earth will have to provide the craft with enough fuel for a 3 million light year journey. He can't possibly risk just giving the astronaut enough oxygen, food, and fuel for just 50 years. And no matter how the astronaut experienced the time, the rocket is still going to have to push, well, I don't know how to say this out loud, but an awful lot of miles to get to the Andromeda galaxy. So I believe in this instance, length contraction is a fallacy. I want to move on to the equivalence principle, and I'm afraid I'm going to find a lot of faults with this too. As I'm sure you all know, it's the force that we experience, gravity on Earth, and Einstein maintains it's equivalent to the pseudo force provided by acceleration in a non-gravitational field. Well, I guess he really means by acceleration of 1g. However, let's investigate this. At the top here, we've got a rocket traveling very quickly, and a pulse is being sent from the tail, and it's being recorded in the nose. Now, because the rocket is traveling forward, during the travel of the pulse, the nose is moving forward of where the pulse was emitted. So it looks like in my drawing that the rocket's growing longer, but what it actually is that the pulse that's sent at 1 second reaches here in 2 seconds, and it goes further now. In 3 seconds, it goes. I'm sure you can see what I'm getting at, and by 8 seconds, the pulse is getting taking much longer to get to the nose. So the the wavelength is changing. It's changing in the opposite way to the example below, where the pulse is sent from the nose to the tail. So obviously, as the pulse is traveling, the tail is traveling forward. So gradually, the distance that the pulse has to travel becomes more and more narrower. And so it shows the increasing frequency. Now we've put these two rockets on Earth. Now, I think it's pretty obvious that the pulse sent from the bottom to the top will stay exactly the same. If it did gradually get stretched and stretched and stretched, there would be a time when it never ever reached the nose. In this example, if it did shrink, as it was shrinking in the 1G thing I just showed you, then gradually the effect of where it is emitted and where it is recorded would come together. They'd be in exactly the same spot, as if if you carried on pressing this and accelerating, the back and the front would be in the same physical space. So this is one big difference between traveling at 1G in a non-gravitational field and it being parked on Earth, static, subject to gravity. And here is a chart of the difference. So here is the rocket on Earth. An astronaut would be held to his seat. If you dropped two balls, they would fall inwards because of the tidal effect. Pulses, as I've just shown, would be constant. No energy expended, and gravitational effect is unavoidable. Accelerating in space, the rocket, again, the astronaut will be held to his seat, but interior items would drop directly downwards. Pulses would diminish in frequency, energy, fuel would be expended, and gravitational effect, you would gradually come out of that gravitational field. In free fall, the astronaut would float. Drop balls would float, pulses would increase in frequency, energy, none need be expended, gravitational effect, none. Free from gravitational influence, the astronaut would float, the balls would float, the pulses would constant, and the energy would be none. So I think you can see there are really big differences in comparing traveling at 1G in a non-gravitational field with being subject to Earth gravity. Okay, so the equivalence principle has given rise to very odd beliefs, especially objects in free fall. So here is a drawing of a lift in free fall, and a pulse of light is sent in this opening here. And then the lift goes down, the pulse of light crosses the lift, and it comes out here. So effectively, we can plot that movement as that for what light has happened. Now, I hope that in my examples above, I have made it clear that I just think light is not affected by the movement of any inertial frame through which it travels. And this is how I see this experiment. The light comes in, the lift starts to fall, the opposite hole drops, and crash, it hits the light. Both observers would see that. This is, see, Einstein claimed that light behaves in a similar way in an inertial frame. He doesn't say that a pulse of light can be affected by the inertial frame through which it passes. This is my view of that. So I'm now going to give you a rather mad example of the use of light and inertial frames. So here we've got a giant, and we've got another observer here on horseback, and we've got somebody who's sitting in a box, which is for him or her, when it is still, it is an inertial frame. And when it is still, a pulse of light is sent from one end of the box out like that. Now, if this giant waves this about, he and this observer will not see this light vary. It will continue in that same line because it is unaffected by this inertial frame. And I'm saying that once the giant has moved from static to moving with this frame, he moves it very, very carefully in a non-accelerating way. So it only accelerates from stationary to movement, and once it's moving, it's kept as an inertial frame. Here we have the view of the inner observer. She is sitting inside this box and he's waving it about. She's moving about with the box. She will see the light appear to move. And the interesting thing about that is that tells her it is she that is moving. Once she can see light that's not apparently traveling in a straight line, but jumping about all over the place, she knows that it's her inertial frame that is in movement, and it is the pulse of light, which is in reality straight, that is telling her that her inertial frame is in movement. Now, this leads me to believe in something really. I beg your pardon?
Well, the inertial frame for the light is the frame that existed at the moment it was released. So if
well,
she continues to,
I have to disagree with that. You see, because
yes, that's a very good example there. The inertial frame for that light is outside the box, and so as far as the light is concerned, what happens inside the box is inconsequential. Its frame is already established at the time it's released.
Yeah.
But this is exactly the same as your green laser light at the beginning.
Yeah, but I'm saying that this light is introduced into the lift.
Right.
And I'm saying that it passes across the lift, and it passes across, and irrespective of the movement of the lift, which is going downwards, it hits this wall here, and this doesn't occur.
Right, but the inertial frame for the light is outside the box, is always outside the box. The fact that something passes in front of the light or behind the light is inconsequential. This elevator could be just as well straight behind the light, and it would not even know that the light exists there.
I absolutely agree. And that's the point I was trying to make with my transparent spaceship with the spark in the middle of it. But of course, that is why this frame that he's waving about is inconsequential to the direction of that light. But it's consequential to the girl who's sitting in it. It's consequential for her because she will see this light moving all over the place relative to her. And that will tell her that it is she that is in movement.
Well, she won't see the light until it reaches her, so that's not possible either.
Well,
she can't see where the light is in transition.
Yes, no, I see what you're saying, but I'm going to for the next thing I want to say is I'm imagining that a pulse of light if it could leave a track in space, it would leave a straight track. I mean, if you imagine, like, you know, a firework going off and it leaves a trail of sparks. I mean, because the point I'm about to make is that if we, and it is just theoretical, it can't be physical, but if we do have a notion of a track made by a traveling pulse of light, this could be the only static thing in the universe. So here is a pulse of light that's just sent out to space from Spain. Now, once it's gone, it is no longer related to the movement of the Earth. So the Earth spins off, and if it could have laid a track, this would be the only static thing in the universe. Because, I mean, if you were to follow the pulse of the light and you were to follow where it came from and were able to draw a line between it, that would be an immovable line in the universe. I'm just going to move on to my last part of my topic here. And I'm going to talk about misleading diagrams that influence our theories of space-time. So here are three commonly viewed images of the effect of masses against space-time, or even against the passage of light. So here we got the Earth, and it is set into, it is made a dish in space-time. Here we got a low mass star, and we've got an image of it. It's often called like a ball in a net, and then you've got a high mass star, stretches it even more. Now, I take exception with these drawings because they are dangerously misleading. So, first of all, it is often used to explain, like a ball in a net, if you roll it around when there's a dish in the net, it would run around a center object like this. And I personally don't believe that that is what's happening. And here I am showing how I think, tentatively, if space-time exists, it should be represented. So even so, I've only represented it in 1, 2, 3, and at the back, 4 planes. 4. So we've got an upright plane here, another one here. We've got ones coming up there. So if space-time exists at all, and if it does affect mass, it won't just affect it dished like this. It will affect it in every single direction. See, even here, that I've not drawn enough directions. It actually should be a sphere of a grid for it to truly represent the effect of a mass on a matrix. And the danger of this is we come to the geometrically defined region of a black hole. Now, it is always, black holes are always drawn like that. I just picked 4 at random. But because this is represented 2-dimensionally, I know it looks like it's 3-dimensionally, but because we are so hung up with the horizon and with gravity and with flat planes, these drawings are because we are hung up in this dangerously inept field, dangerously badly represented field. And here, for example, it's pulling from a high mass star is pulling from the top, like the regular drawings, and from the bottom, just to show that it should be pulling from more than one direction. Here I've tried to draw it pulling from 6 directions, but of course the end drawing, where it's pulling from all directions, would be a globe, would be a spherical environment that was influenced by a high mass, and not just like a funnel, like dropping a ball in a net or a funnel. And the danger of this is how we've looked at wormholes. How wonderfully simple is this drawing? You know, you just somehow join this up, you bend it round and you join it, and you can go to this planet much more quickly. But this is a product of selecting a flat plane of space. Now, this takes a bit of talking about, but to avoid a flat plane of space, I've invented a block of space-time. And So these are the two planets I want to make a wormhole to join. And so I'm taking this piece B and folding it round underneath here, rather like that, rather like this. But instead of being a flat plane, I'm trying to deal with it in more dimensions. So this begs the question, what happens to this area here if you bent it here? What happens to the area that was here when you bent this here? And of course, I just made a kind of magnet shape. But of course, this area doesn't stop. It can go out for all of space-time to be bent. What happens if in this bit that has been bent in my drawing, there's a planet, and suddenly it's been brought closer to here to facilitate this wormhole? But once upon a time, it was near this planet. Now it's miles away from that planet. How are we going to, if we're going to believe in wormholes and the bending of space and space-time and the bending of space matrices, how are we going to make it work if we consider big chunk of space rather than this very unsatisfactory flat piece of space? And also, this covers gravitational waves. Although this looks three-dimensional, these waves are drawn so that they're moving out in a flat plane. And of course, if this event did take place, again, it would expand as a growing sphere. It wouldn't be just like a spiral. So it wouldn't be a wave like it's been drawn, but it would be something very, very different blowing out like that. So we're very near the end of my talk. And you may have gathered that I'm rather suspicious of maths and highly reliant on logic and hopefully clear thinking. And so I want to end this chat by offering you up a little mathematical conundrum, which I think in a very simple way demonstrates how dangerous maths can be in coming to a conclusion. So here it is. Our space pilot that we've been talking about, he stops at a petrol station while he's on the way to the launch pad, and he fills his car up with petrol. He gives the attendant $100 for filling his tank. As he's climbing back into the car, the manager spots this translation, and he says to the attendant, "Hey, you know, these guys are very special. We give them a special rate. That petrol should have only cost him $70. Go and give him the $30 back." So the attendant rushes out. He catches the pilot who's just got in his car, but he's not very honest, and he decides only to give $10 back to the pilot. So he says to the pilot, "Hey, your gas was only $90. Here's $10 back." So the pilot drives away happily. He has actually only spent $90, but the attendant in his pocket has got $20. These two sums come to 110. Where did the extra money come from? So this is kind of meant to be amusing, and it's also meant to demonstrate that that sums and mathematics can be manipulated. So thank you very much for the opportunity to talk to you all. It's an honor to address so many people, and I now open myself up for knives and arrows.
Okay, so who'd like to take the first shot? Who's got a question for Clive? Now, I noticed that some people's microphones does not appear to be working. It's like Harry Ricker, too. I don't see you having a microphone. Also, Roger Anderton, I don't see you having a microphone. So,
I found Franklin, that I had to actually exit and re-enter the forum in order to be able to get my microphone to work. Maybe there's an issue there.
Yeah, so if you can't talk, if you don't see your microphone, you may have to do that. I see Harry Ricker has got his microphone back. Did you do something, Harry, to get your microphone back?
I turned it off. Now I turned it on.
Okay, so you may want to turn on your microphone then.
You don't want to hear me. You don't want to hear me, you know, banging around the room.
Yeah, there's a difference between mute and.
I think just to get to the bottom line here, Do we have any dyed-in-the-wool relativist physicists who disagree with anything with this presentation? I suspect we don't.
I don't have dyed in the
We would
wool,
have heard
but
from them by now.
I don't have much of a problem with time dilation and length contraction, but I don't know how dyed in the wool relativistic that makes me. I look at time dilation and length contraction as due to being the difference between gravitational and mass waves and electromagnetic waves, one being longitudinal and the other being transverse. And through a solid, they travel at different speeds, and depending on the density of the solid and the stiffness of the solid, the ratio of those speeds can change. So if you're comparing light and using light as a standard compared to a mass wave, then you can get activity, you can get relative changes between the two. So I don't have a problem with time dilation and length contraction based on the comparison between electromagnetic waves and mass and gravity.
So I've not managed to convince you then.
No, it totally fits into my images of space time. So
okay.
And as far as you're speaking about the diagram for the gravity well in that, I've never really had a concept of difficulty with that, because I do recognize it as a representation or an effort to represent graphically what is really a three-dimensional spherical change in gravitational strength in a human graphical representation of it. So you're right, it does make, for some people that take it literally, make them think that they can make things like wormholes, which I agree are not really possibilities.
Right.
Can I test my microphone? Can you hear me?
Yeah, Peter, we can hear you.
Yes? Oh,
yes.
Fine.
But get closer, because you sound like you're very far away, kind of echoey.
Okay, I move closer. So I have a remark to this. One moment. So at first, it has to be realized that in special relativity, the time dilation excludes the length contraction. Yeah, so in special theory of relativity from Einstein's 1905 paper, I can make a quote from this paper. Where, yeah, can you hear me? Yes?
Yeah, we can hear you. Go ahead.
Okay. I make a quote from Einstein's paper that because his special relativity paper was written as an adverse possibility to Lorentz Fitzgerald contraction, where Einstein's in 1905 paper, or more exact.
Yes, I have it up, actually. I'm sharing it.
Please. That means that Einstein in special relativity excluded, and he said that Lorentz Fitzgerald contraction is wrong. He refuted it, and he exchanged the opinion of Lorentz and Fitzgerald that purported that time zero result of Michelson-Morley experiment. He explained it with time dilation. Yes, so it means in no case in special relativity we can join the length contraction and time dilation at first.
So you're saying Einstein didn't believe in length contraction?
I can sit there. I can read you I can read you exactly. If you give me 10 seconds, I will find it. I will find it exactly here. So how it is. So
my comment. This is
he
Harry Ricker. My comment.
Einstein exactly the microsound more.
My comment on this would be: it doesn't really matter what Einstein said in 1905. It's what physicists are putting in their textbooks that Clive is commenting.
Who is speaking, please?
This is Harry Ricker. And
Okay.
My point is that what Clive is commenting on.
Your opinion, that's what you said here for the last 3 sessions about the time, space-time. It's absolute nonsense, total nonsense, because time, we cannot make a difference between time and velocity. So we can, in no case, in physics, we can separate the velocity and time so as Einstein do it. It's absolutely ridiculous. We have no space-time, and he alone admitted this. I can make a citation to it, but I will talk with my head. He personally in 1916 and it is I read it now also in 19. It is not known. We knew the.
I'm sorry, I'm not getting the point here. I'm trying to hear, but I'm not sure what.
You are mystified, Mister. You really made a very wrong things for this alliance when you are talking about the time and that we have nothing best than the relativity. It's absolutely wrong. It is the first things with what we have the relativity, because the physics is transferring into manipulation with time. And this you are repeating for the next session here, and it is absolutely wrong. In fact, you are you have no place in this, so you have to go somewhere to mainstream. This is the main. I hear this sentence that we have nothing best than relativity. That is what you said the last 3 times. So you have no place in this society. I'm sorry if you say this, because this is the standard of academics, and when I go somewhere, this is what they say or what they end is. We have nothing worse than reality, because time is not a physical quantity. The physical quantity is velocity and no time. And you cannot separate the time from velocity. Normally said that time and movement and the unit time and unit velocity are in mechanics are fixed quantities, and you can't separate and manipulate it. Let me say what the Einstein did in 1905. Because the velocity of ether and earth, in fact, we don't know how they can rotate. There can be many ways how you can add the velocity of ether and air in Michelson-Morley experiments. And Einstein said that he don't care how these velocity are. So because if there is rotating, if the rotating direction between the ether and air, so of course the supposition of velocity, which was the Michelson-Morley supposition, is absolutely different. Einstein said, I don't care about this, I don't care about physics, I have a time and I will do this physical reality work with time. but this say nothing to us. We want to know the reality. We want to know how the velocity is added and what are the direction of the velocity of Earth and ether. So
I'm afraid
So, well,
I'm lost. I don't know what point is being made here.
I have the 1905 paper up right here, right now. And I seem to have found the relevant bits that Einstein is talking about.
Please take 1907 paper, because this is the paper. That is the paper in 1905 paper. Einstein nothing new about relativity, and he nothing knew what we will done. But
I have the 1905. I'm just paper right up right now. If you look at your screen.
1907 paper. There it is outlined. There explains the web. In 1905, nothing is tell about relativity. He in 1907 paper on 60 pages. I can, if you want to take in collection, this volume 2, there 47. And there Einstein explains his relativity. The name of this paper is it's very funny why we are talking about 1905.
Well, your point remains that Einstein didn't believe in length contraction, although I'm looking right here at this sentence.
From 1905 to 1907, not just the belief, but he explicitly say in this paper that his intention is to make another explanation for the contraction of length. So if I want to, I don't know how many times we have, but it is absolutely unacceptable to work with time, and time is not a physical reality, and it is.
I'm just not getting the point of this.
Yeah, what exactly is your point? I have a hard time understanding what your point is as well.
We in our community, I think, talk about space and time. It's a mystery, and it's a falsification of Einstein. Nobody seriously talk about the time as alone.
No, I'm completely lost now.
Space time is absolutely nothing, but very correct is what was in the presentation. I many times think over that what was now in the presentation.
Has he got the radio on or something, or is it somebody else trying to speak?
Such a mysterium. I very agree. I am very glad that you show these pictures about this the picture, how it is presented by academics, that there is some cone. I agree very with this. There is nothing like that exists. There is a density of masses, which is density of mass, density of earth, density of field, which is symmetrically around big stars or big grade of mass. So I think also about that it could be at one point presented the time that is, but what is stupidity when they to all world are showing this conical picture, and it's absolutely nonsense. And I very agree with you as you told that the wormholes, of course, if you imagine it that it is density of something, let me say space and time around this symmetrical, and it is symmetrical from both with this rising also, or from all sides, from 3D side to the mass, down to the mass or away from the mass, and you have there is no normal way how you can come to a wormhole or something like this. So I very agree And I'm very glad that you presented this picture, because I was also looking if there is something like this, because it's absolutely nonsense to present it that way, that this is some cone, there is a symmetrical gradient of field, let me say your space and time, but of course it is ether, or it is and but by the way, if we are here together, I want to say you that I find a paper Einstein's on from 1924, which is a really unknown paper, but it could be found in the collection. And I read you three where in which Einstein fully accepted the ether. Normally, among the dissidents, we knew the paper from Leiden from 1920, or
I wonder whether we could précis this. I'm not sure whether it's a new presentation or comments on my work.
Yeah, I think we should kind of go back to what the primary subject was.
Thank you.
Yes, well, thank you, Peter, for your comments. So, but I think in interest of time, I want to find out whether anybody else has some comments on Clive's presentation. Like, is there someone here who wants to say that something is incorrect about his presentation, or does everyone just, you're preaching to the choir here, man, right? What do people have to say? Like, let's go back to your experiment there, which I didn't understand at all, where you had your light beam bouncing back and forth between your boxes there.
Okay.
So, my criticism there is that I don't think you're showing anything, because I want to see an experiment which is set up exactly like the way that you showed with the train stations, with the light bouncing out of the box. And the only way to adequately do that is if you literally set up a light beam bouncing up and down and you move the entire box.
Yeah.
And I just don't see that you did that.
Does it work for you, the picture of England with the imaginary two large but carefully placed mirrors that are on a geared track, so that in one's mind you get...
Well, but that's not an experiment. That's, this Einstein dot experiment thing, which I totally don't agree with.
Okay, well, in which case, I think it all comes down to distance. If you were to imagine two mirrors at a massive different distance.
Well, I see, this is my problem. I don't want to imagine anything. I'm looking at your experiment here because I desperately want to believe you, but I don't believe your experiment actually proves anything. So I want to know, on your experiment, where's the laser beam coming from and what is being moved? I mean, to me, your picture looks like you've got this static box and it's like 2.5 units away. And all you've done is that you drag the box like half unit to the right, and then you dragged it another half unit to the right. And that really doesn't prove anything. That doesn't prove to me that if you've got a light bouncing between those two mirrors, that the light is going to bounce out of the mirror.
Right. Well, I don't have any other physical experiment to show you, but I do think that it's very convincing to imagine two mirrors that are so far apart that, supposing you've got two mirrors where it actually takes 2 seconds for a light to go from one to bounce off the other, it must be obvious that during the time it takes that pulse of light to travel, the mirrors could just move to one side.
That it's not obvious that it could be possible that if the light is affixed to the moving frame, that the light could take on the inertial velocity of its emitter. It could. Well, this is the point you're trying to prove, that it doesn't. And the only way to do that is with an actual experiment, to show that when you you would have to affix the point of light to that far mirror.
Yes.
You have to turn it on, and then you'd have to move the frame and show that the light misses the far mirror because it has moved out of the way, is what you would have to do. And the only way to do that is if you actually move the frame at a high rate of velocity.
That's true.
And that's the only way you can actually prove it one way or the other, because it could be that if you did that experiment, that the light does get dragged along.
But that would be counter to all physics, wouldn't it? That would be counter to everything.
No, it wouldn't. It would not, because we know that inertial. If I throw a ball, it stays in motion in the direction that it was thrown at. So you could think that light might perhaps work that same way. But I need an experiment to actually prove
to compare it with a ball being thrown is it's not a good example, because light is very different.
Or maybe it isn't. That's why I need an experiment. I'd like to see this actually done.
I think this is a waste of time to talk about. I mean,
we're talking about experiments to prove relativity or not. I mean, this is how we decide between what's right and wrong. Right? Experiments, that's how we do that.
It's really a thought experiment.
Well, I'm saying that thought experiments are BS. We can't rely on thought experiments. We need to rely on real physical experiments. That's why I was excited to see this particular experiment using real lasers and real mirrors, except that it's not moving, so it doesn't count. But I'm thinking that such experiments can be done. I mean, we can slow light down. I mean, under certain circumstances, we can slow light down to travel about 30 meters per second. Now, at that speed, you'd think that experiments like this would actually be practical, and you could show that when you've slowed light down that much, that you could actually move the frame fast enough to get it out of the way.
So how do you slow light down like that then?
You just put it through a very, very thick or very cold medium. If you look, you can find experiments like that. They've been able to slow the propagation of the light speed down quite a bit. I mean, it's similar to like when we have refraction, when light travels through different mediums, they travel at different speeds. So this is just another way of achieving that ultra slow speed.
Right. I have seen some of those experiments, but I must say I just didn't believe them.
Another thing is that we do have, I mean, I have seen pictures of them bouncing light between mirrors, and apparently our ability to photograph this is sufficiently fast that we can actually see the light going from one mirror to the other in the different frames, which is remarkable. So
do you accept that light can't, having been bouncing between two mirrors, that if you move the mirrors, do you really think that the light would bounce off at an angle rather than bounce directly back?
Well, I don't know. I mean, I've never done it. So this is the question, whether it would do it or not. My guess is that it would bounce out. So I mean, I'm pretty much in agreement with you that it would bounce out, that the mirrors, that if they set up a light clock, that the light would in fact bounce out.
Yeah.
And that's largely because I think that that the light travels relative to an omnipresent ether. It travels in that frame. So I would totally agree that when you do the flash of light, it's completely independent of the motion of the emitter. And that's actually what Einstein really said, which is that the velocity of light is independent of its emitter. So all of that actually matches all the pictures that you have where, it doesn't matter that the flash happened on the inside of the plane or the outside of the plane.
Exactly.
It would propagate exactly the same way.
Exactly.
So that's why I would say that in that case, the light would in fact bounce out. It's just I'd really like to see an experiment showing it actually bouncing out. So if you can arrange for such an experiment, that would be great, a real experiment.
Well, I'll have to try and do it as a movie.
Is this not then a real experiment with this green light? Because I don't quite understand either. The light would continue long enough for you to move the box. Is that correct? Or is that light is that an actual image?
It is an actual image, yes.
Okay, so if I understand, then the left-handmost frame, the light beam is traveling somewhere along the four unit line?
I think it is, yes.
On the table, and regardless of when you move the box, it still remains traveling along the 4 unit line. Is that about right?
That is exactly right.
Okay, so but the light source is actually outside the box originally, correct?
Initially, yes. Yep.
Okay, and so the light source is basically aligned with the 4-unit line.
Yes, I don't. Let me get it up on my screen. Yep.
Okay, so if the light source is actually aligned with the 4-unit line, that light source, that's the frame of reference of the original light being emitted, and that
Yes.
would continue to be the frame of reference for the light, correct?
Yes, that is
And
correct.
so regardless of what you move in front of it, it's going to stay on that 4-unit line.
That is my contention.
Okay, so but the thing is that in the experiment with the moving mirrors, the light source is actually moving with the mirrors, and the moving and the mirrors are already in motion, and
Hang
so there
on,
isn't.
which example is that we're talking about?
Well, this is going to be more of the hypothetical, because this this one here, any one of these here, these light sources are basically moving with the object at the time they're transmitted. So they are more like the light is imparted like the bottom image shows, that it's going to, from the outside, which we're looking at the outside with this green box. We're looking from the outside as an observer from outside the box. We would see the light originate if it were actually being emitted from one of the mirrors of the box, we would see the light originate and move with the box at an angle like the bottom image shows, because that's the reference frame that the light is emitted from, is a moving reference frame. So the light would actually be emitted at an angle and continue reflecting back and forth from each mirror at that angle.
Yes, but only
The
for the
experiment
stationary observer, not for the moving observer.
That's absolutely correct, and that's like the green box. We are the stationary observer. We're on the frame. We're in the frame of the light source, which isn't moving, and the box is moving out, moving. So yeah, that's what basically you're right, Harry. I mean, that's exactly right. So from the frame of, we're looking at it from the bottom frame basically, but the difference is that this image has the light source moving, and the image we're looking at with the green box is actually from the light's emitted from our frame of being the stationary observer. So nothing is in competition with what uh, relativity or what Einstein has said there.
I mean, one way to think about this, I was just looking at that, is that instead of a light beam, if we were shooting electrons, so if we were shooting electrons from the one mirror, then we would accept that the electron would take the velocity that it is currently traveling at when it was emitted. So we would think that the lower diagram here, if we were bouncing electrons between mirrors, that is the path it would take.
Well, there's a difference between sending a line of electrons and one photon, isn't there? If you send one photon, once the source has emitted that photon, the source can do what it likes, and the photon will continue in the passage.
Well, that's the whole question. I mean, until you can show me an experiment one way or the other, I don't know what it does.
Right,
if you think that light is like an electron, then it will do what it does on the bottom diagram.
Hold on. What Clive is saying is, what relativity says is that for the guy in the carriage, the woman, and she's moving along with the train, the light bounces up and down, okay? But for the observer on the diagonal, okay? And what relativity says is that the laws of physics are the same for the two different situations. So the laws of physics aren't different from the person who's moving for the person who's at rest. What Clive has done is shown that these physics books that try to explain this principle basically make a big mess of it and create more confusion than they explain. And so the relativity can't be right, because these people, when they try to explain it, get themselves all balled up in confusion. I think that's what Clive is trying to say. Is that not correct?
It is correct. And I think the difference between throwing a ball across a carriage and getting a pulse of light across a carriage is that when I'm throwing a ball across a carriage, I'm also, because I'm in motion in one direction, I'm imparting that motion to the ball as well as throwing it forward. Whereas the absolute moment when a pulse of light leaves its source, it can't be affected by any centrifugal force. There's nothing in that carriage that grabs hold of light and moves it. There's nothing in between two mirrors that grabs hold of light and moves it with the mirrors. I know you're asking, Franklin, for an experiment, but until one can be done, I think that I'm putting up a pretty credible case.
Is it possible? I mean, the experiment you did with the laser, with the green laser, I don't know. Did you do that experiment yourself, or was that experiment done by others?
No, I did it myself.
Okay, is that laser not movable? I mean, would that, if you were to mount the laser to the box, would that not be the results of that?
If I fitted the laser inside the box such that it moved with the box, then that's for sure the light would stay because I'd be moving the source of the light as it was still continuing to emit light.
So basically, then the light would follow the box.
It would follow the box if the well, of course, it depends on relative speeds. If the box could move, if it was a hugely long box and the light was going from one mirror to another, obviously, if it suddenly moved at the speed of light left, the crossways beam of laser light would drop off.
Yeah, assuming you don't have any acceleration or deceleration of the box's speed, but the box is constant motion, then you would essentially have what the diagram above or diagram on the previous page showed. The only difference being that the laser itself would actually be in the way of the reflecting mirror.
Yes.
Which is your problem. You got to get the laser out of the way of the reflecting mirror once the light beam has begun. I assume that this light beam is sustained within the box because there's something there I mean, because the beam would normally not last that long for you to be able to move the box. What's within the box that keeps the beam going? Like it's a laser within itself, correct?
It's a laser on the edge of a partially silver mirror.
Okay, so once you get the beam in there, then the laser action continues within the box.
It does.
The excitations of the gases within the box continue to be a laser of itself, right?
Yep.
Okay, because if it was an evacuated box, we obviously wouldn't even see the beam because there's no reflection off, nothing to reflect off of.
No, it's only reading because there was smoke there.
Yeah, and there's also no atoms within the box. There have to be atoms within the box to be excited to keep the beam moving.
Okay.
Okay, is that correct?
Well, it's just done in plain air, so yes.
Yeah. Okay, because I'm just trying to see why it is that the beam's sustaining itself so long yet emitting enough light to us for us to visually see it. That would be.
Yeah. I think the laser beam is constantly on.
I think that there's a disadvantage with this slide is that everything is so small.
Okay.
Whereas if we look at the previous slide, I know that Franklin won't like the idea that it's not a real experiment, but if you look at the one, can I move it? Or
yeah, you can move it. You have control.
Sorry, I think we're getting close to the end too here. So
yeah, we got the last 5 minutes, so we're going to go through this one.
Actually, I can't move it. Obviously, this is a point of contention of whether or not light in it can be moved by its reference frame, which is pretty fundamental, actually.
I mean that would be the main bone of contention. I mean, this experiment would work. This experiment would work if you attach the laser beam to the far mirror, and then you took this and put it in a big truck and you drove it at 100 miles an hour and see whether the light started to bounce out.
It would probably.
It should not hit the other end exactly at the same location as it does when it's still.
It would be such a minuscule deflection, though, because of the speed of light. 100 miles an hour is nothing. I think my misconception was I thought that the beam was shut off, the laser light was shut off, and the beam continued on its own, reflecting through the mirrors. But there's always a beam being projected through the partially silvered mirror on the near end, and that was my misconception. So I see now that you know, there was too much of a simplicity.
Yeah, there's just a beam being launched down to this
right,
fourth marker, and he's just basically dragging the box across it.
Yeah. Okay. That. Yeah, that's not of much significant use then, I guess, in that sense.
Yeah, that's how I was saying that I don't think that that was a very significant experiment. But we are getting towards the end of the presentation here. So I wanted to thank Clive for coming here and showing this. I mean, it is an interesting possibility that the light would bounce out of the box, but I think it's still in his court to show that that's what would actually happen. And I think he's shown some interesting possibilities for how some of these so-called time dilation or length contraction things either probably shouldn't happen or happen in different ways. And I think that at the very least gives us something different to think about, because all of these things, you know, the thing with the relativity, I think, is that a lot of these things are done as thought experiments. And I mean, like this airplane experiment, this is something we could probably actually do now with ultra fast electronics. And like you can do things like slow the speed of light down to something practical, so that you don't need humongous distances to show that these things happen. And I think slowing light down is probably a perfectly fair thing to do. It's still light. You've just slowed it down through some kind of medium.
Anything, Franklin, because it would just show that the speed is whatever the medium is that's slowing down. So if you use a medium to slow down light, what would that prove? You'd only prove that the light is a function of the medium.
Well, maybe that's what we need to prove then.
Franklin,
I don't think you know what you're talking about, Franklin.
I mean, I personally think that that is actually what would happen, that if you did, because we've seen that in the, there's a Fitzhugh effect, that if you shine light through moving water, it will take on the velocity of the water. So certainly the frame of reference that light goes in is in fact dependent upon the speed of the medium. I mean, that particular experiment proved that.
Actually, I'd like to suggest that GPS has to use the one-way Sagnac effect for a moving receiver, and that is essentially disproves the second postulate right there.
Yep, it could, but well, we do need to wrap things up today. So once again, this has been the CNPS Saturday morning chat with Clive Tickner. And that was a great presentation, Clive. And if anyone else would like to have their own presentations about this subject or anything else, I invite you to send me a topic like Clive did, and I'd be glad to have you on the upcoming science chats. So, but I think that will do it for today, and invite you back the same time, same place next week. So watch out for the announcements.
Thank you very much. Thanks.